civilization was desperate. They had tried everything. They'd built galaxy-spanning observatories to capture every wavelength of light pouring in from the entire observable universe. They'd crafted ingenious devices to peer into the microscopic, then subatomic, and then quantum realms. They'd even explored and colonized vast swathes of the cosmos, great arc ships traveling between galaxies over time spans of billions of years. They were, without question, the most powerful civilization the universe had ever seen. But it was still not enough. For after untold millennia of effort, they had finally come to the conclusion that their universe was not alone, that there were infinitely many more, that what we see as the vast and almost incomprehensible cosmos is just one tiny, insignificant bubble, floating in an infinite sea. The existential dread of this realization did not bother the civilization. By now, far removed from their genetic origins, they were used to dealing with a giant, cold, uncaring universe. The real problem was one of measurement. The presence of an infinite multiverse brought with it seemingly insurmountable difficulties. Difficulties in evaluating problems. For example, a relatively simple question: were they alone? For the observable universe, this was fairly straightforward. They could work it out by scanning every single star and every single galaxy. But even though they had figured out how to access the other regions of the multiverse, their studies had shown them that the rest of the universes within the multiverse were not just numerous, they were infinite. And this meant that they couldn't measure probabilities. Was their universe common or rare? Was their type of carbon-based life form 5% of those in the multiverse or 95%? It was impossible to say if there was an infinite number of universes. Every percentage read zero in their calculations. How many intelligent species inhabited the multiverse? An infinite number. But the multiverse also contained an infinite number of empty universes. Any finite amount of information they had gathered amounted to zero. Despite their millennia of effort, they literally knew nothing. Their journey had begun eons before in their dim and distant past, taking their first cautious steps into outer space by building far-flung probes and grand off-world observatories. They eventually developed their own Kardashev scale, mastering all the energy on their home planet, then their solar system, galaxy, and beyond. Over the ages, they had taken to reshaping entire planets, systems, and galaxies into powerful experiments and exquisite laboratories, simultaneously peering out into the cosmos and down into the microcosm. But how far could they ever go, and how much could they ever discover? Were there cosmic barriers they could never pass, information hidden in the darkness that they could never reach? What were the ultimate limits of the universe? In 2011, nomads traveling the Sahara Desert found a literal piece of Mars. The meteorite, named Northwest Africa 7034, had a fascinating secret, one which many different news outlets reported. However, modern-day news reporting can be overwhelming, chaotic, and hard to work out what to trust, which is why Ground News has been a big help in my research, and they've kindly helped to make this video possible. This platform gathers the world's news in one place, so you can compare coverage and verify your information. Indeed, using Ground News, I discovered that this meteorite showed evidence of water on Mars over 4 billion years ago. It was great that I could see this information from dozens of news sources worldwide, as well as in bullet point form through their summary feature. Each of the news sources also come tagged with information on context, like whether the publication leans left or right, who owns the publication, and a very helpful factuality rating. Interestingly, more than 90% of the sources on this story are rated highly factual. And so I encourage you to visit ground.news/HOTU or scan my QR code if you're looking for a quick and easy way to stay fully informed on any topic. Make sure you use my link to save 50% off unlimited access to their Vantage plan, the same one I use. Indeed, this is their biggest discount of the year, whether for yourself or as a gift. it had all started with patterns. The creatures of the civilization had noticed long ago that there were certain special rhythms in the world around them. Seasons changed on a predictable cycle. Dark clouds looming on the horizon meant that a storm was coming. The appearance of special stars meant that it was time again for the planting of crops. And so they created physical markers to signify these important rhythms and developed rituals to remind themselves of their importance. Slowly, agonizingly, over the course of centuries stretching into millennia, they began to discover deeper patterns. They found laws that could apply across the universe, formulas that governed physical processes regardless of their location in space and time. They discovered the fundamental constituents of matter, breaking down elements into atoms, atoms into particles, and particles into subparticles. They mastered the intricacies of gravity and quantum mechanics, diving deep into complex mathematics that revealed how both tiny particles and massive galactic superclusters behaved. They deduced what energized stars and supernovae, heartbeats and hearing. They learnt it all. They became sophisticated and powerful, wielding the secrets of the universe to their desires. They invented science, and it was beautiful. But this was just the beginning. How far could they stretch these ideas? How long would it take to reach Kardashev Type 1? Nikolai Kardashev didn't set out to imagine the scales of possible alien civilizations. Instead, he just wanted to be an astronomer. Born in 1932 in the Soviet Union, his parents were initially members of the Communist Party, but were arrested when he was just 5 years old. He lived as an orphan. By the time his mother was released, he'd already graduated from university. At Moscow State University, Kardashev focused on radio astronomy, which at the time was a new and exciting field of research. He was prolific in his scientific career, joining the Space Research Institute and serving many roles in the International Astronomical Union, a transnational effort that helped connect scientists despite the tensions of the Cold War. But his entrance into public consciousness came from a 1964 conference in Armenia, where he presented a now famous paper on communicating with alien civilizations. To estimate a civilization's ability to broadcast radio transmissions, Kardashev assumed that more advanced civilizations would be capable of harnessing greater and greater amounts of energy. Drawing by analogy a comparison to hunter-gatherers collecting by a campfire to modern society splitting atoms for power, Kardashev estimated that civilizations more advanced than our own would go on to capture the energy equivalent of an entire star, or even an entire galaxy. This would give them even greater abilities to communicate across the vast distances of the universe. And so in his paper, he briefly sketched out a simple classification scheme, which came to be known as the Kardashev scale, in his honor. A Type 1 Kardashev civilization would be able to harness the power of its entire home planet. A Type 2 Kardashev civilization would be able to harness the power of its entire sun. And finally, a Type 3 Kardashev civilization would be able to harness the power of an entire galaxy. Paper complete and presentation given, he returned to his main focus of astronomy. But the public's imagination would not be finished with Kardashev and his energy scale. However, before we dive into intergalactic empires and push scientific advancement to its ultimate limits, it is important to remember that the journey had to start somewhere. Survival. Humanity arose in a world that was complex, confusing, and hostile. Our best defense against that world was to learn, to apply our unique intellect, to deploy our ability to imagine alternate possibilities, and to reason through deliberate choices. One of the earliest examples we have of the emergence of science in humans is in the form of a slim ivory tablet dated to at least 32,500 years ago. On one side of the tablet is the silhouette of a man, with legs astride and arms outstretched, a figure resembling the constellation Orion, one of the most well-known constellations found in cultures around the world. and on the other side, a neat rose with 86 notches carved out. 86 is an interesting number. From the vantage point of the cave where the tablet was located, the stars of Orion were below the horizon for roughly 86 days every winter, and 86 days subtracted from 1 year gives a rough estimate of the human gestation period. And so did these ancient people devise some method of keeping track of time based on the disappearance and reappearance of Orion? And did they make a connection between that length of time and the length of a pregnancy? We can only speculate what their motives were, but clearly these prehistoric people were beginning the journey towards some kind of science. One of the most prominent philosophers of science, Karl Popper, argued that some myths represent the first ever form of scientific theory, a kind of proto-science that generated testable ideas that eventually evolved into scientific thoughts. Stories of creation, of how the world came to be, stories of forces, of how wind and rain and rivers have the properties they do, even stories of emotions, explanations of why we feel the pain of a loved one's passing or the joy of the birth of a baby. Cave paintings, like those at Lascaux in France, depict the world of our ancestors, animals and hunters, the important sacred rhythms of their lives preserved on the walls so that lessons could be shared with each new generation. Eat this, not that, be careful in the wilderness, this is how to be an adult in our society. And so our ancestors learned how to wage war, how to fashion weapons for hunting and for killing, how to settle disputes, how to create laws and govern themselves, how to turn the sounds of their speech into marks on stone and paper so that their words, their thoughts and ideas could be transmitted across space and across time. And as our knowledge grew, human societies became ever more sophisticated. Specialists developed, and in almost every culture, a certain class of specialist arose, the astronomer. It was within that class, the astronomer, that the first threads of modern science began to appear, because it was the astronomers that first applied a relatively new trick in their quest for knowledge in the universe: mathematics. Indeed, some of our earliest recordings of the sky include mathematical models to predict celestial events. Take the Saros cycle. If you happen to see a solar or lunar eclipse, then there will likely be another one 223 lunar months from that event. But it was one person in particular that took mathematics in a new, unexpected direction: Galileo Galilei. Galileo was born in 1564, and while previous thinkers had applied mathematics to the study of the heavens, Galileo was among the first, and by far the most prolific, in his application of mathematics to every phenomenon. According to Galileo, the book of nature is written in mathematical language, and the symbols are triangles, circles, and other geometrical figures, without whose help it is impossible to comprehend a single word of it, without which one wanders in vain through a dark labyrinth. Galileo was one of the first to use mathematics to discover facts about nature that ran against common sense. For example, common sense dictates that heavier objects should fall faster than light ones. Indeed, the great philosopher Aristotle reasoned that heavier objects had a greater affinity for the Earth. But Galileo used mathematics and careful, repeated observations to realize that all objects fall at the same speed, unless wind resistance becomes a factor. This discovery was perhaps the birth of modern science, where evidence and experimentation led the way to new knowledge. Indeed, one of the philosophical foundations of science is empiricism, that evidence rules the day. You can have any idea you want, but ultimately, evidence and observation determine whether that idea has any merit, or if that theory is valid. Mathematics also gives science two important tools. One, mathematical models provide handy, concise summaries of natural phenomena. E equals mc squared is easier to remember than explaining the whole thing. It also allowed scientists to follow a logical progression in their trains of thought. With mathematics, a scientist can form a hypothesis and know for certain that consequences of that hypothesis will be true. To illustrate this idea, let's think about lightning. For millennia, philosophers had debated about the true nature of lightning bolts. For most cultures, lightning was a sign from the gods, usually one of displeasure. The ancient Greeks knew of some electrical phenomena, such as the electric sparks that form when rubbing amber on cloth. Indeed, the word electricity comes from the Greek word for amber, and while some philosophers argued that lightning was a scaled-up version of this electricity, others argued that it was more akin to a bolt of fire. And it wasn't until 1752 that the matter was settled. Flying a kite in a thunderstorm, future founding father and all-round polymath Benjamin Franklin was able to pass current from the storm into a Leyden jar, a simple kind of battery, demonstrating that lightning was made of electricity. With that confirmed, other experimenters, like Charles Augustin de Coulomb, discovered a simple force law relating electrical charge. Mathematical insights by Carl Friedrich Gauss and Michael Faraday revealed that the influence of electricity is better described by electrical fields. And a half-century later, James Clerk Maxwell would unify the description of the electric field with that of the magnetic field, and discover that light itself was made of electromagnetic waves. A chain of reasoning, careful investigation, and mathematical insight would go all the way from lightning bolts to the true nature of light. A surprising and unexpected result. And so through the scientific method, we have been able to discover the workings of many of the most mysterious phenomena in nature. Storms are caused by heat transportation in the atmosphere. Volcanoes are caused by magma chambers venting to the surface. Lightning is caused by static discharge between clouds. Diseases are caused by microscopic pathogens invading our bodies. The list goes on and on. And one of the most powerful parts of the scientific exploration of the universe is that our knowledge is always updating and evolving. As an obvious example, we've updated our understanding of gravity many times, starting with the basic concept invented by Galileo and into the Newtonian revolution, where he realized that gravity was a universal force of nature, and then, after 2 centuries of refinement and expansion, Einstein changing our view of gravity again, seeing it as a consequence of the deformation of space-time due to the presence of mass and energy. Our understanding of its true nature has shifted dramatically. Even today, we know that another refinement in gravity is on the horizon, one that incorporates the physics of the quantum world. Through science, humans have acquired more knowledge in a few short centuries than we have in all previous millennia combined. Our understanding of the universe has exploded. And yet, despite all our accomplishments and our slaying of the mythical dragons of old, the universe is still full of mystery and the unknown. It seems, despite our scientific prowess, that we have not yet even scratched the surface of what we can know. And so what is our ultimate limit? To what extent can we use these remarkable scientific techniques to explore the universe around us? How much can we ever know? Perhaps our greatest limiting factor is the biological systems that support and create our own thinking. Our brains, as sophisticated as they are, can only capture and retain so much information at a time. Speed reader Howard Stephen Berg claims to be able to read 25,000 words per minute, although his claims are disputed. In 2020, Emma Alam of Pakistan memorized 410 random words in 15 minutes. And in 2015, Rajveer Meena of India demonstrated to the world that he'd memorized 70,000 digits of pi. It's difficult to assess the capabilities of the human brain. The nearest metaphor we can use is computing, but the human brain works in a very different way. However, we can make some rough analogies. The total memory capacity of the brain, for example, is somewhere around 2,500 terabytes, 1,000 times more than your typical home computer, but far less than our most powerful supercomputers. However, our brains are also extremely efficient at sorting through the blizzard of sensory data constantly streaming in. Our conscious minds can only process around 40 to 50 bits of information every second, and from that trickle, we are able to be aware of our surroundings, make complex decisions, and fashion incredible leaps of insight and imagination. And on top of these limitations, on a cosmic scale, our bodies are comically fragile. We are ultimately limited by our DNA. We must regularly consume food and water. We must ensure that we get adequate rest. Indeed, the longest that anyone's ever stayed awake is roughly 19 days. The human body can only exist in a narrow window of circumstances. The human mind can only operate within a finite range of capabilities. In the end, our biology dictates our limits. Even the smartest or strongest person still requires the same basic mechanisms. Sodium ions must still move across semi-permeable membranes to activate connections between neurons. Electrical signals must travel up and down the nerves at finite speed. Hormones must spread throughout the body to maintain homeostasis. All of these mechanisms are written into us as the product of billions of years of evolution. There is no trick of genetics or accident of birth that can expand our capabilities beyond that. We are trapped, either in the slim biosphere that supports our kind of life on the surface of the Earth, or in a ready-made capsule capable of temporarily supporting us within the depths of space. Wherever we go, we must always carry our biology with us. And so in our quest for advancement, the question has to be asked: is there a way to go beyond the limits of the flesh? The experiment was finally ready. The civilization had spent generations, 1,000 years by their reckoning, in its construction. In their quest, they had achieved what we humans would dub a Kardashev Type 1 civilization, harnessing the equivalent power of all the solar radiation arriving on their home planet. In the process, they had colonized their entire solar system, with societies and cities on every planet, from the sun-baked innermost worlds to the distant icy moons. They had sent countless synthetic emissaries out into the void between the stars. They had discovered the fundamental forces of nature, the strange rules of the quantum, and more, and put that knowledge to work in the construction of fantastic, seemingly magical to us, technological devices. But they had also run into familiar limits. They had discovered long ago that the fundamental forces of nature merge together at extremely high energies, inaccessible to any planet-bound laboratory. And so to peer even farther into nature's mysteries, they constructed a particle collider the size of their solar system. Scavenging every last remaining uninhabited asteroid and scraping layers off distant, unwanted moons, they constructed a ring of superconducting tunnels orbiting their star. By their calculations, the device would have the energies needed to break the quantum gravitational barrier and directly access the Planck scale, where space and time themselves break down. Over the centuries, the experiment developed the aura of a religion. The occasion of the first test runs of the collider were accompanied with great pomp and circumstance, long-winded speeches, blessings, and prayers. And finally, after generations of work and anticipation, they activated the experiment, ready and willing to peer into the heart of nature. Our brains, with their 100 billion neurons and 100 trillion synaptic connections, are the most complex structures in the known universe. And so as we found that our thirst for more knowledge was never quite sated, we developed tools to extend our thinking. Prior to the theory of germs, doctors had assumed that cholera, a horrible disease that causes life-threatening diarrhea and dehydration, was caused by miasma, or bad air. However, in the mid-1800s, the physician John Snow suspected otherwise, but could not prove it. And so, in 1854, when an outbreak of cholera struck the Soho neighbourhood of London, Snow deployed a relatively new technology that would seem obvious to clinical researchers today. A map. A simple dot map showing the clusters of cholera cases. He used this dot map to find the centre of the clusters, a water pump on Broad Street. Evidence in hand, he convinced the neighbourhood authorities to remove the well pump handle. And with that, the outbreak ended. His astute use of the simplest of instruments, a map, saved many lives. And so technology does not need to be complicated in order to be effective. But as we learned about the inner workings of the natural order, we could build more powerful technological tools to probe further and learn even more about the world around us. We invented devices that extend and enhance our normal senses. We created telescopes that bring the distant universe into our laboratories, beginning with Galileo's transformation of a curiosity toy sold at markets into a refined scientific instrument. His first telescope achieved only 8 times magnification, a power superseded by simple modern binoculars, but with that magnification he was able to reveal the mountains and boulders of the Moon, the satellites of Jupiter, and the multitude of stars that make up the band of the Milky Way. Indeed, with each new iteration of the telescope came new discoveries, culminating in the 1920s with the Hooker telescope. With that telescope, Edwin Hubble was able to observe individual pulsating stars within the Andromeda Nebula, discovering that it was instead a galaxy sitting millions of light years away. And while telescopes continued to get larger on Earth, they were limited by the distortions of the atmosphere. Space telescopes, while smaller in diameter, had a more pristine view of the cosmos. With a mirror diameter of 6.5 meters, so large that it had to be cleverly folded up to fit inside its rocket, the James Webb Space Telescope achieves a resolution of around 1/10 of an arcsecond. That's hundreds of times more powerful than the human eye, capable of reading the details of a coin placed 40 kilometers away. And the most powerful proposed telescope is called the Solar Gravitational Lens. Using the bending of starlight due to the sun's gravity, an instrument placed about 540 astronomical units away from the sun would be able to observe images magnified to a resolution of 10 to the power of 10 arcseconds. At that resolution, it could paint a detailed portrait of the surface of any exoplanet within 100 light-years of Earth. And at the other end of the spectrum, we have created microscopes to expand into view the unseen world around us. Today, the most powerful microscopes rely on quantum tunneling to provide precise information down to an astonishing resolution of 0.05 nanometers, which enables us to map out the distributions of atoms and molecules within materials and create high-resolution portraits of even the smallest of biological organisms. Most recently, we have also developed computing as a third branch of scientific investigation, standing alongside theory and experiment. Through computer simulations, we have watched as synthetic universes evolve over billions of years. We have peered inside the hearts of stars as they die in fantastic supernova explosions, and we've observed as proteins fold together and perform their vital functions. And so, technology has advanced rapidly over the 20th century as humanity has continued its quest for information about the world around us. Indeed, the total information content currently available to humanity in the form of electronic storage is estimated at around 175 zettabytes, or 175 trillion gigabytes, and on an annual basis, the entirety of humanity consumes roughly 5 times 10 to the power of 20 joules of energy. And so while most of that energy does not go to storing information, if we want to upgrade our current technology, and if we want to acquire more data about the universe, we will need to harvest more energy. And so what would be the most effective way to do that? If we were to cover the entire surface of our planet in solar panels, we could capture roughly 4.4 times 10 to the power of 16 joules of solar energy every single second. In less than 3 hours, we could potentially capture enough energy to fulfill our present-day energy needs for an entire year. But if we wanted to do even more, we would have 2 choices: capture more solar energy or travel to an energy-rich environment in the galaxy. To capture more energy, we could follow the suggestion of visionary physicist Freeman Dyson, who envisioned ripping apart entire planets and converting them into a shell surrounding the Sun. These so-called Dyson spheres could capture more of the solar energy that currently simply blasts away into empty space. For example, if we were to convert the entire mass of the Earth into panels or pieces of a shell roughly 1 kilometer thick, we could capture 0.0004% of the entire solar output. That seems small, but it's orders of magnitude more than the 10th of a billionth of the solar energy that the Earth currently receives. Of course, this kind of mega engineering does not come without its own energy costs. It takes energy to rip apart a planet. With kilometre-thick panels, it would take tens of thousands of years to recoup the energy investment spent in unbinding the Earth to transform it into solar arrays. Considering that we've observed no Dyson spheres within the galaxy, perhaps a smarter option is to pack up and move. Black holes offer a great home for an energy-hungry species. Their small size and rapid rotation stir up space-time around them, and clever arrangements like the Penrose mechanism can be used to extract energy from that rotation. At that scale, we could turn entire planets into data storage warehouses. We could convert entire solar systems into observatories. We could send far-flung probes to the edge of the galaxy and beyond. And indeed, returning to high-energy physicists, we can find one of the clearest examples of scientific and technological advancement running hand in hand. Our attempts over the last century to crack open reality itself. Beginning in the 1930s, physicists realized that they could use electric and magnetic fields to accelerate charged particles to higher than normal energies before smashing them into pieces, combing through the debris in the aftermath to see just what they were made of. They started to peer into the world of the subatomic. Ernest Lawrence, working in Berkeley, California, was one of the first pioneers of these particle colliders, creating a 4-inch diameter cyclotron that could achieve energies of 80,000 electron volts. After World War II, when most high-energy particle physics was taken over by the development of atomic weaponry, researchers created the Cosmotron at Brookhaven National Laboratory in Long Island, New York, and achieved energies of 3.3 billion electron volts, going on to discover a new class of composite particles, known as mesons. The Tevatron at Fermilab, outside of Chicago, Illinois, reached peak collision energies of 980 billion electron volts, and with those energies in the 1990s, verified the existence of the top quark. And in 1991, construction began on the enormous superconducting supercollider in Texas, but 2 years later, the project was shut down due to budget cuts. If completed, it would still remain today as the world's most powerful collider. Instead, the holder of that title is the Large Hadron Collider at CERN, located at the border of Switzerland and France, which took nearly a decade to build and cost almost $5 billion. Achieving energies of nearly 14 trillion electron volts, thousands of scientists from around the globe participate in the experiment and through their work have confirmed the standard model of particle physics and the key role of the Higgs boson in particle interactions. Particle colliders have been a huge success in helping us pull apart the subatomic realm, but they are also a clear example of the limits of our current technology. Though the Large Hadron Collider can reach incredibly high energies, to be able to probe the Planck length and search for experimental evidence that could help us prove or disprove current theories of quantum gravity, a hypothetical framework that would combine general relativity and quantum mechanics, we would need a particle collider able to reach energies 10 trillion times higher. And so while we continue to grow ever more powerful, we're already seeing our own limits. If we want to explore further, we have our work cut out for us. We will have to develop radical new technologies that go far beyond the scale of what we can even imagine. We will have to expand our engineering might to encompass not just planets or stars, but entire galaxies. The fleet consisted of over 10,000 ships. After spending generations developing ideas, comparing and contrasting different techniques, exploring and exhausting all options, the civilization had ultimately decided that there was no single best way to move amongst the stars. And so they attempted all of them, all at once. Some of their civilization began construction of mighty generation ships, miniature worlds in their own right, capable of sustaining large populations for eons. Others crafted spry, single-occupant vehicles, powered by planet-bound beams of light to loft them to a pre-selected star. but most opted for some arrangement in between. Medium-sized ships containing many, but not huge amounts of passengers, with most of their occupants in a state of torpor, while automated systems guided the craft. Indeed, it took almost everything the civilization could muster, but they had no real choice. They had depleted the energies and resources of their system. They had to go elsewhere in search for answers. They had outgrown their home, pushed past the boundaries of a Kardashev Type 1 civilization. It was time to venture out and move towards Kardashev Type 2 and beyond. And it turns out, the key to unlocking the stars rested in an unexpected place: hummingbirds. There are hundreds of known hummingbird species, which as a group are the smallest living birds. Most of them live in the year-round riches of the tropical rainforest, but roughly a dozen species spend their summers in North America. And every single year, as the air starts to cool and plants and flowers prepare for winter, these hummingbirds begin a great journey, migrating to warmer climates for the winter. Among these species is the rufous hummingbird. At an average size of just over 7 centimeters long, at the end of every summer it undertakes an annual migration of over 6,000 kilometers, traveling from Alaska to Mexico, only to return the following spring. And one of the strategies that enables this miraculous flight is the hummingbird's extensive use of torpor, a state of reduced activity related to hibernation. In torpor, the hummingbird enters a state of deep sleep, dropping its body temperature by half and slowing its metabolism by 90%. And this torpor, or hibernation-like state, will be necessary if we desire to travel among the stars. Because, quite simply, they are very far away. Launched in 1977, the Voyager 1 spacecraft is currently nearly 25 billion kilometers from Earth. It is humanity's farthest-flung spacecraft and is truly now in interstellar space, having crossed the heliopause, the region where the sun's solar wind gives way to the interstellar medium, in 2012. Traveling at a speed of over 60,000 kilometers per hour, Voyager 1 will continue its journey amongst the stars, eventually becoming just one more body orbiting around the center of the Milky Way. And so, if we had placed an infant on board the journey of Voyager, it would have been middle-aged by the time it reached interstellar space. By the time that Voyager reaches the inner edge of the Oort cloud, the diffuse collection of icy debris orbiting the Sun that serves as the home of the long-period comets, that person would have been long dead, as that journey will take another 300 years. By the time that Voyager crosses the outer edge of the Oort cloud, 10,000 more years will have passed. And if Voyager was aimed at Proxima Centauri, our nearest neighbor star, it would take over 35,000 years to reach its destination. Indeed, as a species, we are only now getting used to interplanetary distances, but we are not even slightly prepared for the enormity of interstellar, let alone intergalactic distance scales. The Canis Major Dwarf Galaxy is the nearest galaxy to us at 25,000 light-years away. It would take Voyager roughly 749 million years to reach. All current far-flung spacecraft accelerate only a few times. Once at launch, with most of their energy expended simply by escaping the Earth's gravitational grip, and then in space, our craft do not carry all that much propellant, just enough to repoint themselves if they drift off course. For additional acceleration boosts, spacecraft can use gravitational slingshot maneuvers, stealing some momentum from planets and giving it to themselves, boosting them to higher speeds. But out between the stars, that simply won't be an option. And so, simple physics presents hard limits to our ability to travel. Accelerating spacecraft, no matter the means, requires energy. And in the vast, expansive deserts between the stars, energy is hard to come by. So any craft will have to either coast at constant speed, like our current craft, or carry a source of energy with them. Because of this fundamental limitation, to reach further into the universe ourselves, we have two choices: large but slow, or small but fast. In the 1950s and 60s, a collaboration of scientists working with the United States Air Force, DARPA and NASA investigated the possibility of a spacecraft accelerated by the most powerful and compact source of energy available to us: nuclear weapons. Called Project Orion, the concept was to ignite nuclear bombs behind a spacecraft. A large plate would absorb the blast and, by conservation of momentum, push the spacecraft forward. While the project only had interplanetary missions in mind, the researchers did find that a 10,000-ton spacecraft would only require roughly 800 bombs to accelerate a payload of 5,000 tons to Mars, or 1,000 tons to Saturn in less than 3 years, opening up the tantalizing possibility of extending this concept into an interstellar mission. However, the project eventually fizzled out as the engineers could not overcome the numerous technical challenges, leaving the only object to be accelerated into space by nuclear propulsion, an iron lid, welded above a shaft as an attempt to contain a detonation called Pascal A in 1957. Scientists estimated the lid sped into the atmosphere at a speed 6 times the Earth's escape velocity. But despite the abandonment of Project Orion, future generations may revive the concept, or find other clever ways of accelerating spacecraft to manage the voyage across the stars. One such hypothetical concept, which for now sits firmly in the work of science fiction, is the generation ship. Also known as the world ship or arc ship, the basic idea is to not bother trying to get to other stars as quickly as possible. Instead, the ship would become an isolated bubble of humanity, with a large population living and working generation after generation, deep within interstellar space, and only reaching their destination tens of thousands of years into the future. Of course, such vessels would be incredibly complex, and the voyage fraught with danger, but with such means, a civilization could slowly and steadily advance among the stars. Perhaps not very far, a steadily expanding sphere of maybe a few dozen light years across, but even that would enable the exploration and colonization of hundreds of worlds. And the civilization might not even have to build it themselves. We know that natural debris, shards and pieces left over from the formation of solar systems across the galaxy already wander from system to system. Indeed, in 2017, one such piece, named Oumuamua, briefly entered the inner solar system before quickly making its way back into the depths. A patient civilization could just wait for the right opportunity and hitch a ride, transforming the wandering space rock into a suitable habitat for the journey. But the only known way to make the interstellar journey faster is to make the spacecraft as small as possible. And in recent years, the Breakthrough Starshot initiative based out of New York has proposed such a craft. It relies on a light sail, a thin membrane that reflects light and pushes the main body of the craft forward. The reference design of the Starshot concept is to use a square light sail, a kilometre on a side, powered by a 100 gigawatt laser for 10 minutes. The spacecraft could achieve up to 10% the speed of light, reaching our nearest neighbour star well within a human lifetime. There is one catch, however. The Starshot spacecraft itself can weigh no more than a gram. Unless an advanced civilization wants to flood the galaxy with paperclips, they're going to have to find a better way to travel. And so, just how far a motivated species could travel is presently unknown. A few light years would allow them to visit nearby stars. Tens of thousands of light years could get them across a galaxy. Millions of light years would let them make the leap between major galaxies themselves. But despite all the challenges and obstacles, if they are able to achieve extremely fast velocities, then ironically, physics does allow them one reprieve: time dilation. We know that moving clocks run slow, that from the perspective of outside observers, the closer an object gets to the speed of light, the slower in time it appears to progress. This is part of the interconnection of space and time that undergirds our universe. The passage of time remains normal for any passengers. After all, thanks to relativity, from their perspective, they could rightly argue that it's them that are standing still and it's the rest of the universe that's moving. Of course, for this time dilation to have any meaningful difference, then a spacecraft must come as close to the speed of light as possible, which presents its own challenges. But if a civilization could somehow harness the energies to do it, the entire galaxy would be at their fingertips. For example, if a spacecraft could maintain a constant acceleration of 1g, roughly 10 meters per second, inching ever closer to the speed of light as it travels, it would take nearly 30,000 years to manage the trip from the solar system to the core of the Milky Way, from the perspective of outside observers. For the passengers on the ship, however, that massive undertaking, crossing half the width of the entire galaxy, would be completed in only a few years. But this is an extreme example, and would require truly extreme energies. In general, it seems likely that to take advantage of the wider universe, we would have to drastically alter our biology. Humans currently live for roughly 80 years, the blink of a cosmic eye, though through cultural traditions and written records we're able to preserve information and transmit it to the future for our descendants to use. But if we are to pursue the greatest of cosmic mysteries and attempt to consume all the information available in the universe, we will have to find ways to extend the capabilities of our own human brains and extend the lengths of our lives, long enough to make the journey between the stars in search of ever greater sources of energy. Indeed, it may be possible to develop systems that allow us to liberate our conscious minds from the prisons of our bodies. This would allow us, or at least some version of us, to travel among the stars without the need for oxygen, water, food, and vast energy resources. We might be able to develop small spacecraft housing individuals, or even entire communities, existing in a low-energy torpor-like state in the long journeys amongst the stars, and awakening once more resources and energy are available. But, even with alien or artificial superintelligence, there will still be limits. At the end of the day, we all live inside the same universe, bound by the same laws and the same physics. Try as we might, the cosmos itself puts hard limits on how far we could ever go. They called it simply the machine. It had taken them eons to build, so much time that the original founders of the project, indeed even the planet where the founders had come up with the idea, had long since vanished from the historical record. But the purpose, the goal of the machine had persisted through the ages, through revolutions and rebellions, through political splintering and harmony, through bad times and good. The civilization had long ago mastered all the technology they needed. They devised crafts to ferry them across the gulfs between the stars. They could control the force of gravity. They could create intelligence as sentient as they were. They were now firmly classified as a Kardashev Type II civilization, with each one of their capitals capable of consuming the energy output of an entire star, enrobing it in a networked mesh of solar panel arrays. But the machine was their greatest project yet. They'd sent themselves and their electronic probes far and wide throughout their home galaxy and found not a trace of any other living species. As far as they could tell, they were alone. And they desired to know if the entire universe was just for them. And so a small group of them, distant descendants of their first scientists, proposed a plan. A scan of every single galaxy in the entire observable universe, capturing every detail at every wavelength of light with as much resolution as they could muster. Enough information, enough knowledge that they could determine once and for all if they were truly alone in the universe. Eventually, the machine spanned the entire galaxy. Robotic missions set to work on far-flung solar systems, transforming entire planets into lenses, antennae, power sources and communication arrays, each system becoming a vast, multi-wavelength observatory. Each observatory got to work, and once completed, taking roughly 10,000 years for its survey, began sending the collected data back. These data streams took over 100,000 years to complete transmission. Entire planets were converted into data storage warehouses. Black holes were used to power the computational processing. This would be it, a census of the entire universe. The total absorption of every scrap of knowledge that the cosmos would have to offer. And then, only then, could the civilization rest. If we project our technological achievements far into the future, assuming that our current pace of advancement continues, we can imagine all manner of fantastic engines of scientific discovery. We could design particle accelerators that loop around the solar system and beyond, achieving energies far above what we can with the Large Hadron Collider. We could build telescopes positioned in the outer solar system that leverage the gravitational lensing of the Sun, using it as a magnifying lens to amplify our images of distant stars and galaxies. Far into the future, we could even capture solar energy, or the rotational energy of more exotic objects like neutron stars and black holes, to provide the power necessary to run overwhelmingly powerful computers capable of simulating physics at all manner of scales, perhaps even simulating the universe itself. But despite our seemingly endless future potential, there are limits inherent to the cosmos. The speed of light, the age of the universe, the number of particles, the rise of entropy. Hard boundaries that the laws of physics simply will not let us pass. And of course, at some point, if we continue our quest for knowledge far into the deep future, we will acquire every bit of information available in the entire universe. For the uncomfortable truth is that there is only a finite amount. In the 1920s, astronomer Edwin Hubble revealed that the universe is expanding. On average, every galaxy is getting farther away from every other galaxy, except for the occasional random merging due to gravitational attraction. And over time, cosmologists realized that this discovery revealed that there was a finiteness to the universe. One finiteness was in time. Prior to Hubble's discovery, astronomers had assumed that the universe was infinitely old, that it had simply existed statically forever into the past and would continue to exist in largely the same state forever into the future. But the Big Bang put a finite age on the universe, or at least on our universe. The second finiteness was in the spatial extent of the universe. In truth, the universe could be infinitely big, but the expansion history of the cosmos introduces a horizon that limits our ability to access it. The cosmos is only so old, roughly 13.8 billion years old in fact, and light only travels at a finite speed. This means we can only see a small portion of the entire universe, like holding a torch in a pitch-black room, because there's only been so much time for light from distant objects to reach us. This limitation is encapsulated by the concept of the light cone, which is a projection of the limits of the spread of influence and information in both space and time. For example, if you send out a light signal, it takes time for that message to reach distant destinations. If the sun were to shut off at this very moment, it would take 8 minutes for that information and ensuing darkness to reach the Earth. If the Andromeda Galaxy were to somehow suddenly disappear right now, we wouldn't find out for another 2.5 million years. Expanding this concept to the entire universe tells us that the cosmos could be, and probably is, far larger than we could ever possibly observe. This means that there is information in the form of more galaxies and stars and events that will remain forever inaccessible to us. Their light, their information will simply never make its way to us, and whatever secrets they hold will remain out of even our most eager of gazes. In fact, because the universe is constantly expanding, the most distant objects in our observable bubble are already receding away from us faster than light. What we see now was light sent to us billions of years ago. By now, the galaxies are so far away that over time they will slowly fade away from view. In an expanding universe, the amount of things we can see shrinks with time. And so all the information we could ever acquire about the universe is contained by those bounds in space and time. Almost 14 billion years into the past, and roughly 42 billion light-years in any direction. And this confinement introduces a fundamental uncertainty into any measurement at large scales. known as cosmic variance. Many processes in the universe happen through random chance. They were seeded many years ago by some bit of fundamental physics, but the actual evolution of the system proceeded through the roll of a dice. For example, the Milky Way galaxy is located here, in this region of the universe, and it has a particular mass, a particular star formation rate, a particular merger history, and so on. While the physics of the early universe powered the gravitational engines that would eventually give rise to galaxies, those forces didn't dictate exactly where the galaxies would appear. The Milky Way could have been anywhere. And so measurement of large-scale structure of cosmos-spanning fundamental constants, like the total amount of dark matter or dark energy, must take this randomness into account. There is therefore a fundamental uncertainty drawn from the fact that we can only ever access a small portion of the complete universe, and can't measure its entirety. For example, if someone only shows you a handful of randomly selected cards from a full deck, you'll reach an unavoidable uncertainty when you try to assess the total number of cards of any suit. And so, there are clear limits we encounter on large scales, and yet on the other end of the measurement scale, we run into fundamental uncertainties of a very different kind. To begin with, there is the thick veil of fog that is the Heisenberg uncertainty principle. First discovered in 1927 by quantum grandfather Werner Heisenberg, it was initially envisioned as a simple limitation of experimentation. If you wanted to study a subatomic particle, for example, you looked at it, which meant you had to bounce photons off of the particle. Normally in the macroscopic world, this is no problem. Photons do carry energy and momentum, but it's so slight that it makes no difference. A bear is still charging at you regardless of how bright a light you shine on it. But subatomic particles are small enough to react to photons. If you really wanted to nail down the position of a particle, Heisenberg realized that you needed a photon with a very small wavelength, a photon which would therefore have a correspondingly high energy. But that high-energy photon would then knock the particle. By the time the photon returns to your measurement device, you would have a very accurate idea of the particle's former position, but now you have no idea of how quickly it's moving. But if instead you use a low-energy photon, you'll know that you haven't disturbed the particle much, but the large wavelength of the low-energy photon means that you have correspondingly less precision in your measurement of the particle's position. Heisenberg realized that you couldn't have your cake and eat it too. You can't measure with infinite precision both the position and momentum of a quantum particle. But this wasn't just a mere measurement limitation where we could devise some clever trick to get around it. It turned out to be baked into the fundamental mathematics of quantum mechanics. Despite this, in a series of debates, Albert Einstein himself tried to find ways to escape the uncertainty principle. But every time his opponent, Niels Bohr, found a flaw in Einstein's thinking. In a series of public letters, Einstein devised various contraptions involving springs, slits, clocks, and more to argue that the uncertainty principle was merely an illusion created by our lack of complete knowledge of the quantum world. And yet, each time, Bohr was able to take a careful, detailed analysis of Einstein's arguments and find either an incompleteness in his train of thought or a full accounting of where the uncertainty principle would still hold. In the end, Einstein would grudgingly concede that there were limitations to our knowledge of the universe, but to his death, still held that quantum mechanics was itself an incomplete description of nature. And so, there is information in the quantum world that we simply cannot access, and another way this manifests is through the probabilities inherent in all quantum processes. In the macroscopic world, as long as you know the state of the system, a summary of every particle's position, momentum, etc., and you know the laws of physics, then you can predict with absolute certainty how that system will evolve into the future. But quantum systems do not obey the same set of rules. If you know the state of a quantum system, you can only assign probabilities of how the system might evolve into the future. And it is the equation bearing the name of Erwin Schrödinger that tells us how to calculate these probabilities. They take the form of waves. Each and every particle in the universe has a wave attached to it. The wave may be real or imagined, that's up to different interpretations of quantum mechanics. Where the wave peaks, you have a strong chance of finding the particle the next time you go looking for it. And where the wave troughs, you have a low chance. That is the maximum amount of information that you can extract from a quantum system. A map of where the particle might be, not where it will be. But the boundary of this limit is actually sometimes hard to discern. For example, we normally associate the limits of quantum mechanics with subatomic particles, well below the threshold of everyday experience. But in 2019, a team of physicists led by Yakov Fine at the University of Vienna achieved the seemingly impossible. They were able to extract the wave nature not of a single subatomic particle, but a monstrous molecule containing 2,000 individual atoms. Their work showed that with the right experimental setup, the fuzziness and uncertainty inherent in quantum calculations can be blown up to surprisingly large scales. And lastly, there are regions of the universe where information exists, but may be forever locked away from us. Inside black holes, and in the past. Indeed, black holes are such excellent keepers of knowledge that they are the densest collection of information possible in the universe, yet we cannot access almost any of it. The most salient feature of a black hole is its event horizon, an invisible boundary that prevents the escape of anything that has ever fallen in. Whatever made the black hole, whatever the black hole has consumed during its dark life, is hidden behind that veil. You can visit and access that information if you wish, but you must do it in person by crossing the event horizon yourself. And once you do, you will never escape. You can continue to receive messages and information from the wider universe as light continues to pour in, but you cannot share your revelations with anybody else. And there is the uncomfortable fact that once you cross an event horizon, your time is up. In a finite amount of time, as measured by a watch on your wrist, you are guaranteed to strike the singularity, the point of infinite density that defines the black hole. And so whatever knowledge you gain from accessing the black hole's dark heart will die along with you. All that remains are three parameters visible to the outside world: the mass, angular momentum, and charge of the black hole. All else is darkness. And as for the past, as far as we understand physics, and indeed understand the very fundamental concepts of space, time, and causality, what has happened in the past is forever lost to us, inaccessible except through our memories, artifacts, and the present state of the universe. We can guess and speculate and reason all we wish, but the instant that a moment passes, it slips behind that grey horizon. What is not preserved is truly gone. On large scales, microscopic scales, across invisible boundaries and through impossible tunnels, there are whole realms of the universe we simply could never access. And so what is the ultimate limit of information we could access? What is the true cosmic limit? To begin with, there are somewhere between 500 billion and 2 trillion galaxies in the observable volume of the universe. If we were to somehow halt the expansion of the cosmos and instantly record every single one of them, that would be it. That would be all the galaxies we could measure. Ever. Any question we asked about galactic evolution would have to be limited by that set of information. All told, those galaxies contain somewhere around 200 billion trillion stars. Again, the same problem arises. Think of any possible question that you have about the nature of stars. If we were to complete our observations of every single one, measuring every property we could manage, including each star's position, velocity, spectrum, and so on, then that would be it. Eventually, you could start asking questions that could not be answered by that limited dataset. And we can also approach the problem from microscopic scales, hoping to squeeze more useful information out of the universe. There are approximately 10 to the power of 80 protons in the observable universe. We could, in principle, work hard enough to measure the precise location and momentum and quantum state of each and every one. We could repeat this exercise for all the electrons, all the neutrinos, all the dark matter particles, and so on. We could then complete the exercise by measuring the properties of every single photon, of which there are approximately 10 to the power of 90, the vast majority of which originate with the cosmic microwave background, the light left over from when the universe transitioned from a hot, dense plasma to a neutral state when it was 380,000 years old. Each one of these particles and photons carries with it a certain amount of information, but even that would not be a full accounting of the limits of our universe. That's because all these particles are built from quantum fields, which exist as vibrations in space-time itself. The vibrations can exist whether there is a particle or not. Therefore, we need to probe deeper, even deeper than fundamental particles. We need to peer into the space between them, and as we go to smaller and smaller scales, adding up the information as we do, we finally would encounter the ultimate expression of the Heisenberg uncertainty principle: the quantum foam. In one sense, the quantum foam can be viewed as the ability for the quantum field to briefly steal energy from the vacuum of space-time, creating a particle in the process, and then quickly giving it back before anybody notices. In another, complementary view, the quantum fields that together build up our reality simply have a fundamental energy associated with them, a baseline vibration that is present even in empty space. And we reach that scale at the so-called Planck length, which is around 1.61 times 10 to the power of minus 35 meters. This number does not come from any fundamental theory, but rather exists as a mashup of important constants like the speed of light, the strength of gravity, and Planck's constant. However, at these scales, our normal senses of space and time break down, as what we normally consider smooth and featureless space-time gives way to a roiling mass of turbulence. While there may be usable information below that scale, that is well beyond known physics. And so for all intents and purposes, the Planck length serves as the resolution limit to accessible knowledge in the universe. And so this all means that to get the total information contents of the cosmos, we divide its observable volume into an incredibly large number of units delineated by the Planck length, and within each of these volumes we inquire about its state, for example, the energy levels of all the quantum fields. And according to several advanced theories of physics that relate the entropy of the universe to its information content via a formulation pioneered by American scientist Claude Shannon, we can estimate the information bound of the universe by simply assigning one bit of information to each one of these Planck-sized cells. And that estimation leads to a total information content of the universe of somewhere around 10 to the power of 120 bits. Though speculative, no matter the approach, knowledge in our universe has a bound, a limit. As advanced as we someday hope to become, we cannot break those limits. And even if we were able to acquire all that information, to probe every secret that the universe holds from us, to search in every hidden corner, to measure everything measurable, would we still be missing something? Is there another way to view the universe? When first suggested, the idea frightened the civilization. For years it was argued against, ignored, dismissed, and forbidden. It was heretical, anathema, abhorrent to every value and virtue that the civilization in all its different forms had ever held dear. But as the ages passed and they could find no other route to new knowledge, the idea became more alluring, more tempting. By now, the civilization was very old, ancient even by their own unfathomable standards. They'd long ago left their homeworld, indeed even planetary existence itself. They spanned the length and breadth of their home galaxy, and finding no other sentient life within it, moulded and shaped that galaxy as they pleased. They were now Kardashev Type 3, capable of capturing and using the energetic output of the entire galaxy. But they had long ago run into a boundary that they could not cross, no matter how advanced their technology. They could not imagine being anything but themselves. They began to wonder if it was possible, perhaps, that their consciousness, advanced as it was still somehow bound by the rules of their ancient genetic heritage, and if it was this that was making them blind to the true nature of the universe. They had invented machines that could think on their own, hoping that these synthetic brains could outwit and outthink them, bringing a different kind of consciousness into the universe that could see it, think of it, explain it in a different way. But the machines were just mirrors of themselves. Faster, true, and sometimes unrecognizable, but still the same. And in this long despair, the idea emerged. They found a young world nestled in some forgotten corner of the galaxy. A world wet with water, a world orbiting a stable star, a world rich in chemicals. They then seeded that world, touched it in small and invisible ways. A tweak here, an adjustment there, just the right modifications to turn a soup of chemicals into the ingredients needed for life. But not just any life. Encoded in those first dancing chemicals, written in the way they moved and organized themselves, were the seeds of sapience. With enough time, enough patience, the life that arose on that planet would eventually become intelligent. But the designers of the plan did not know what kind of intelligence would arise, and that was the point. They didn't know how these creatures, billions of years into the future, would perceive the world around them, how they would interact and evolve, how their own genetics would limit their understanding in some areas and expand it in others. They didn't know what knowledge the creatures would discover. They didn't know if there was another way to access the universe. Content, the designers of the plan slumbered. And as they slept, they dreamt of what they might learn from us. There may be hidden limitations to our ability to acquire knowledge within the universe. Even science, as powerful, flexible, and expansive as it is, may not be the best tool to squeeze out every last drop of information. For example, humans acquired knowledge and put it to work well before the development of the modern scientific method. Science exists as a branch of philosophy, and philosophy has a long and storied tradition stretching back centuries. Mathematics itself is a pursuit of knowledge, of abstract logical systems that may or may not be applicable to situations in the real world. But the axioms that mathematicians prove to be true are still true. It's still knowledge, even if it's never expressed in a physical system. Similarly, philosophical traditions like skepticism have drilled deep into the nature of knowing itself, asking if we are truly learning about the universe or simply creating fantasies that suit our imaginations. In other words, we can know things even if we can't verify that knowledge through science. If we are to ask what makes for a just society, or what ethics are and how we should employ them, then that is real knowledge with a real-world impact, and that is knowledge not acquired through the scientific process. But even purely within the realm of the natural world, big questions remain, and it remains to be seen if we could ever grapple with them. The nature of time, the mystery of consciousness, the bare fact of the existence of a universe, and so on. All these questions and more continually slip our grasp as we try to wrestle with them and make their answers known. And so perhaps we may indeed need a different perspective, a way to break free from the prisons of our own type of mind. There is fervent debate occurring now within the philosophical and computer science community about general artificial intelligence, the kind of AI that can reason and think and create similarly to humans. It might be possible that intelligence is simply intelligence, and that once a system possesses it in the form of conscious awareness, that's it. Creatures or computers might be dumber or smarter or slower or faster, but that they are all the same kind of intelligent and perceive the universe in roughly the same way. But it could also be that machine intelligence would be vastly different from our own, capable of not just making decisions that don't make sense to us, but also perceiving the cosmos through an entirely different framework. The most recent debate on the topic has come with the rise of generative AI algorithms, such as ChatGPT. But these algorithms do not construct sentences in the same way we do. They use vast libraries of texts to predict which words commonly follow others, giving them the ability to string together sentences. Those sentences sound surprisingly human, but this approach is not capable of reason or able to understand the meanings of the words it creates. But there is a sort of intelligence there, one highly unfamiliar to our own. Some people claim that continued development along these lines could lead to a totally different kind of intelligence, one that is capable of reason and understanding, but based on entirely different frameworks. Indeed, a powerful machine AI system could come to recognize deep truths about the universe, truths so sophisticated that it would be nigh on impossible for it to explain them to us, because our own human minds only operate in a single, limited way. But of course, there is also the possibility that they too would be limited by their forefathers, trapped within boundaries we unwittingly passed down. And finally, even if we could answer these questions and all the others that we haven't even thought of, even if we could access the complete and total universe free from any bias or biological limitation, even if we could examine it from another perspective, another point of view, we would still have to grapple with one thing: the final hurdle that the super-advanced civilization could never cross. Infinity. The first known philosopher to engage with the concept of infinity was Anaximander, a Greek who lived around 600 BC. He argued that the universe was unbounded or indefinite, a way of thinking that we today would translate to infinite. Later Indian philosophers like Surya Pranyapti would provide the earliest treatment of different classes of infinity, arguing that a line of infinite length was inferior to a plane of infinite area, which in turn was less than a form with infinite volume, all of which was superior to a structure with infinite expanse in infinite dimensions. But Greek philosophers would later reject the concept of infinity, arguing that its possible existence led to all sorts of troublesome paradoxes. For example, Zeno of Elea questioned the nature of movement. If you cover half the distance to a destination, then half the remainder, then half again, and so on, could you ever really be said to reach your goal? Despite this, in mathematics, infinity was clearly useful, and infinity's close cousin, the infinitesimal, was used by both Isaac Newton and Gottfried Leibniz as the basis for calculus. Indeed, today infinity represents a broad class of entities in mathematics, and thanks to the foundational work of Georg Cantor in the late 1800s, we now know that there is more than one kind of infinity. In fact, there are an infinite number of infinite numbers. But while we may have mastered the mathematical concept of infinity, infinities still cause chaos in our understanding of the wider universe. For example, one of the roots of this problem of infinity comes from an unexpected source: the Big Bang. Our current best theory of the earliest moments of the universe is called inflation, a hypothetical event where the cosmos grew rapidly in size in a short amount of time. And buried within that theory is an intriguing possibility: that our universe, even the wider universe, far beyond the bounds of our observable horizon, is but one of many, embedded in the floating sea of a multiverse. Each universe would have its own laws of physics, its own range of particles and fields and forces, and its own particular arrangement of matter and energy. Indeed, if we are to take the multiverse concept to its infinite extreme, then there is, somewhere out there, an exact copy of you. In fact, because of the way infinity works, there would be an infinite number of copies of you watching an infinite number of copies of this video. And this is what would introduce what is known as the measure problem. With an infinite set of universes inaccessible to us, it would be impossible for us to make judgments about how rare or common, how unique or widespread anything we have in our universe is. The problem is that there would be an infinite number of every kind of universe. If you pick one property of our own universe, like the rarity of life or the true nature of dark energy, we could not say what would apply generally across an infinite multiverse. There would be an infinite number of universes abounding with life, and also an infinite number of desolate, empty universes. While there are sophisticated mathematical techniques that can allow us to judge the relative weights of different kinds of infinities, we simply don't know which of these kinds of rules would apply to a multiverse. And so, we would be swimming in a sea of ignorance. We couldn't even learn the core tenets of physics, the laws that operate not just within our own particular universe, but govern the behavior of the multiverse writ large. We could gather every scrap of information accessible to us, from the earliest moments of the Big Bang to the outermost edge of the visible universe, and we could use that to come to a remarkable number of conclusions, but beyond that, we would be ignorant. If this multiverse exists, and its own existence may be something forever beyond the bounds of evidence, then the implications are clear and stark. Of course, we may someday discover a new kind of physics, one that allows us to travel from one universe to another to explore the varieties that the multiverse has to offer. In those journeys, we would have much to contend with, strange and exotic playgrounds that defy even our imaginations, perhaps even universes that operated under completely different kinds of physical laws. But even that would not help us with the challenge presented by the measure problem. For in an infinite multiverse, it would take an infinite amount of time and infinite amount of resources to explore them all. No matter how far we got, no matter how much we traveled and hopped from universe to universe, there would always be an infinite number of universes just beyond our horizon. Whatever we learnt would always be a finite amount of an infinite quantity. 0%. This infinite multiverse concept may be wrong, but if it is correct, then the existence of multiple universes in parallel to our own presents the ultimate limit to our knowledge. We would be able to become masters of our own universe and nothing more. We could learn everything there is to know about our cosmos and nothing more. Infinities just have too much weight, too much power for us to ever overcome. And so, our quest for knowledge in the universe presents us with innumerable challenges and limitations. We are limited by our own senses, by our ability to perceive the world around us. We are limited by our imaginations, by our cleverness and our ability to think new thoughts and view the world in different ways. We have technological limitations that prevent us from exploring the entire scope of microscopic and cosmic scales. We might even have more fundamental limitations, born from our own genetic heritage and the structure of our brains. But all those limitations are in principle surmountable. We can develop new ways of thinking, create new technologies for pushing past barriers, and explore the cosmos in a variety of ways. But with all that effort and endeavor, we could never escape the ultimate limitations presented by the universe itself. We can never, truly, know everything. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.